Welcome everyone. Thank you so much for joining us today for our second Fluorescent Friday. The Inter-Society Color Council is creating Fluorescent Fridays as a platform for university students from different perspectives to network with color professionals and fellow students and to explore cutting-edge information about color's multidimensional nature and its application in the world. If you're interested in being part of this, check out our website. Some of the benefits of becoming a member are listed in this slide. Our long-term goal is to build a global student chapter that positions color as a multidimensional STEAM model: science, technology, engineering, arts, and math, and provides up-to-date color research by scientists, artists, designers, industry professionals, and students working at the university level. Driving this initiative forward is a realization that color communication across disciplines requires a commitment to building new bridges in order to share resources and create new opportunities. Today, we are to celebrate the month of Valentine's Day. For that reason, this Fluorescent Friday session will focus on the color red. We will discover red's dynamic role in perception, light, communication, color measurement, psychology, and branding. What is the perfect red? How red is defined in a variety of disciplines? We have 6 guest speakers. Get your questions ready for a Q&A session. You can write the questions in the chat as we go, and then at the end of the presentations, the panel will answer your questions.
All right. So my name is Dr. Lina Cardenas, and I'll be the first speaker today. I'm an assistant professor at the School of Design at the Pontificia Universidad Católica in Chile. I consider myself a bridge between science and design. I teach textile studio, research methodologies for design, and undergraduate research projects. For my presentation, I'll be talking especially about 3 approaches to red. What is a unique red, the perception of red in Chilean observers, and the abundance of red in pre-Columbian textiles. Now, the experience of color is very personal. For this, I want you to look at the black dot, the next slide, yes, for 30 seconds. Did you see color? Is there color now? Well, this was just an exercise to warm up and to start talking about how color, it's a various personal experience that we even see color when there is no color. Unique hues are defined as hues that cannot be described other than using their own name. For example, a unique red is neither yellowish or bluish. Investigations have been performed trying to identify unique hues locations in the psychological color solids to model color model systems. Now, we have to remember that when we talk about color, there are usually 3 dimensions. So a unique hue is just the name that cannot be called yellowish or bluish, but it can be a light or dark hue, or a saturated or unsaturated color. Color experiences are personal, but a glimpse of the difference can be obtained when selecting samples for a given observer represent unique hues. Now, if we go to the next slide, if you scan this QR, you can go and experience yourself the difference that can be obtained when selecting samples for a given observer. Which of these blocks would you pick as your unique red? Let's take into account that this is not a perfect reproduction of the original samples since we're using multiple devices. You don't have to answer right now. We'll come back to this at the end of the presentation. As a part of a small study in North Carolina State University while I was a PhD student, we carry out an experiment using a complete rotating hue circle of Munsell chips with constant lightness and chroma. The only thing that was changing was the hue. 33 naive observers participated in the study with a total of 102 observations. Observers were asked to identify their unique hue. As you can see, the circle, and they were asked to define which one was green, yellow, blue, and red. I'm not gonna talk about the results of all the colors. I'm just gonna show the results for red. This shows the average perception of red for that particular lightness and that particular chroma. The sample that was selected, it was 2.5 R as the average for all the unique hues, and the range of colors, as you can see, is very wide. We also noticed that we had a little bit of difference between females and males. For all the hues, you see that there is a little bit wider range of colors for females than males. That's the other thing. That's what I can say about the unique hues. The other thing that I want to talk about is the perception of red in Chilean observers. A lot of the studies on semiotics of color around the world have been carried out with European, North American, and Asian participants, and only few have considered South America. In the case of Chile, these studies are almost non-existent. As a part of an undergraduate research project in design, one of my students carried out a study with 185 participants. The study was carried out in two parts. The first part, the participants were asked to say everything that came to mind when they saw the name of the color in the screen and in the first 10 seconds. Then for the second part, when we had all the concepts, we summarized the concepts, they were asked to select a chip sample from the Munsell book of chips that better represent the color in their minds when they were asked about the concept. 8 main concepts were identified for red, 6 of which are in high agreement with the studies around the world. We have anger, strength, love, blood, heat, passion. The only ones that were different is that red was associated with Chile and also with apple. We believe that that's because a lot of the national elements that are from Chile are red. For example, the national flower is a red flower, and also the soccer team selection has the red t-shirt. Yeah, like I said, 6 of these were in full agreement with other studies. The only difference was with the apple in the When it came to the sample that they selected, they came up with this sample that represented red as the main component for all the concepts. One thing that was very strange is that the red was the only color where people selected only 2 samples for all of these concepts. And this one has the majority of observers chose this color as the representation of all those concepts associated with. So this is the sample that for Chileans is red. Now, for my last item, I will talk about research carried out by Soledad Oces. It's a colleague of mine that works at the School of Design. And what I did is I helped her to obtain data representing pre-Columbian textiles from the northern part of Chile. She was having difficulty trying to specify the color in the textile pieces that she was studying. The Munsell chips and Pantone are used usually for these types of studies, but the colors they were finding in this on those pieces, they were really far away from what they would see, what they perceive with their eyes. So what they ask is that since the weather conditions were in the north part of Chile are very dry, they were in very good conditions, and we were able to carry out a spectral measurements with the spectrophotometer in 42 pieces. That's basically it. I'm just saying that from 42 pieces, 230 hues were found. And out of these 203 hues, 83.7 correspond to red. This is because there's a good correlation between blood and fertility with the earth. That's it. Thank you. All right, since it seems like my connection is good now, I can continue with the presentation. Our second guest is John Seymour, also known as John the Math Guy. He's a color science consultant and an adjunct professor at Clemson University, an applied mathematician and color scientist with 19 patents. He has 22 years of experience in advanced product research and 10 years of experience as scientific programmer. He's going to talk about color linguistics. John, the screen is yours.
Thank you. So I want to start off with something we should all recognize. This shirt here, Gilligan's shirt, is red, and Ginger's hair is not red. It's orange. I mean, you could call it ginger, but really the color is orange. These two actresses, the color of their hair, we may argue about whether that gives them a feisty attitude, but really something that is indisputable is that their hair is not red. This is the only person I know that has really red hair. And there's some bozos like that have red hair, but that's not common. How about this animal? This is a red fox. Well, it's not a red fox, it's a brown fox, but we call it a red fox for some crazy reason. Here's another animal that's called red. This is a red panda. Very cute animal, but it's not red. And actually, it's not a panda either. Poor, unfortunate, cute thing. How about this? The red roan cow. Is it red? How about these red labs? Are they red? Next up, we have the only red dog that I'm aware of, Clifford. He is red. How about this animal here? The robin redbreast. Is the robin redbreast, does blah, 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 blah. I don't think he's got a red breast. How about this? The red-headed woodpecker. Yes, this one is indeed a red animal. How about the red snapper? Lovely fish, delicate flavor, but it's not red. Next up, we have a red herring, and this red herring is not red, it's brown. How about red wine? One of my favorite foods. Is it red? How about these red grapes? Are they red? How about the red onion here? I would prefer to call it a Bermuda onion because it is not red. Next, we have the red pepper. And yes, that one is indeed red. The chili pepper, the cayenne pepper is another pepper that is red. They dry it out, they grind it up, they make it into a spice, and that spice is reddish orange. How about red meat? Yes, that is indeed red. Red cabbage, it's full of antioxidants, wonderful crunchy flavor, I love it, but it's not red. How about red beans? Good golly, why do we call those red? Ruby red grapefruit, is that red? The redcoats are coming. And of course, we have the redwood forests. The redwood tree is called a redwood tree because the wood inside of it is brown. Why? Why do we have all of these chromolinguistic misnomers? Why do we call these things red when they're not really red? I have an explanation for that. The explanation goes back to the research of Kay in Berlin, started in 1969 and then continued in 1976. One of the findings from that research is that colors when languages are first created, they have two names that are what we would call a color name. And those two names are white and black, or at least light and dark. All colors that are lightish will be called white. All colors that are dark will be called the black. And those color names stick with them. Now, when languages start to develop, the first color that generally is distinguished from white and black is red, and all colors that look reddish are what we would call warm colors, are all called by that name red. Eventually, more and more color names, basic color terms is what they call them, get developed out until we go through 7 phases. And here we have 11 different basic color names that are in the English language today. Now, here's my explanation of how this misnomer occurs. I'm going to suggest that these characters here were all given their name back when red was the predominant name that went to orange. In other words, orange had not been distinguished from red yet in the language. And I'm going to further explain that these items that are purple were named before purple got distinguished from red. If you're interested in further reading on this, there's a YouTube video that I think it's really great on the work of Berlin and Kay. And all of these blogs were written by me going back 6 years. I can hardly imagine that, about linguistics and color. And that's it for me. All right, next we have Michael Murdoch coming up. He's an assistant professor in the Munsell Color Science Lab at Rochester Institute of Technology. He teaches colorimetry, psychophysics, and programming. He's also worked in industry on many color applications, including computer graphics, displays, and LED lighting. Take it away, Mike.
Thank you, John, for the introduction, and thanks everybody for coming today. Hope this is interesting about red. I'm happy to talk to you today about red light, which is very important to a lot of things that we use. So red light can sometimes be just red on its own, right? Stoplights, traffic lights, lasers, that kind of thing. But red gets much more interesting when you start mixing it with other colors. So if you start with a red spotlight in a dark room, you add a couple other colors to that, green and blue, for example, and you can mix those together to make white in this case, or just blending pairs of colors to get secondary colors. This is the idea of additive color mixing, and red is usually a critical piece of that. Additive color is kind of the opposite of subtractive color. So if you have a piece of paper and you're adding ink to it, you make colors with subtractive dyes like cyan, magenta, and yellow, and maybe black and some other things. But if you're working with light, you start from a black room and you start adding components to it. And usually red is one of those components. So these three are shown balanced so that the mix of the three of them is white. But of course, when you're mixing these lights, you might decide to mix a little bit of less of red in. You get something that's biased more cyan. You could, of course, dim the green and blue and leave the red strong, and you get a mix that's more pinkish. And you can imagine that by changing the relative balance of each of these components, you can make a lot of colors. And of course, that's exactly how we make displays and other things work in our life. The display screen you're looking at right now is doing this kind of color mixing in it. So it's nice to show these like spotlights as if they're separate, but usually we just zoom in on the mixture itself, and there it's pink. And when you look at it this way, you can't distinguish, you can't know that it was made from red, green, and blue components. And that's sort of a critical aspect of our vision system. We have this trichromatic system where you can make the combination of red, green, and blue look like a different color indistinguishably. So additive color mixing is really just that. It's really math. So here's doing math with colors. And here I'm showing the sort of scaling of a red. So 0.8 times full red is an almost bright red. 0.6 times full green is a slightly dimmed green. 0.2 times blue is a kind of a dim blue. If you add those all up, you can do this in Photoshop or whatever, you get, in this case, something like a beige color, right? And you can do that math equation. That's the same thing that I'm showing with these spotlights. And your display doesn't really work with spotlights, but it does work with little pixels. And they are not this big, they're not that big, they're super tiny, and they're close enough together so that they appear to mix to your eyes, right? So zooming out on our on the electromagnetic spectrum, we have wavelength here as a physical quantity, and our spectrum that we've all seen if you've ever looked at a prism or seen other things shown here. Now, of course, these colors aren't exactly what you get from a prism because they're being shown on the screen, but that's the general idea. And you can see that there's a whole region here that looks quite red. By the way, these are the Roy G. Biv colors in kind of right to left order in this case. And these line up, you can line up with these our eyes' color sensitivities. So the three curves here are the sensitivity of our short, medium, and long wavelength cones that we all have in our eyes. And what you see here is where these curves are high is where you're really sensitive. And so you're sensitive to red light, especially in this region where your long wavelength cone is very sensitive and your medium and short are lower or even not sensitive at all. You may also have noticed that out here beyond red, it goes to black. And that's really because these sensitivities trail off to 0 over here. So these wavelengths are not really light anymore. They become infrared energy, which of course is invisible. Same thing on the other end, there's ultraviolet, but we're talking about red today. So where's red on this diagram? One answer is it's right here in the middle of this region of the spectrum. Here I'm showing a spectral power distribution of something like an LED red, which has a lot of energy here and a little bit less on each side. And that really strongly stimulates this long wavelength sensitive cone. This might stimulate the middle one a little bit and the short one not at all. So this curve that I'm drawing here is a spectral power distribution of red. You could be asking, what's the perfect red? Could be hard to answer that. One way to think about it is that the spectral bandwidth of that red affects how red it is, or the purity of the red. If you have light at all wavelengths, energy at all wavelengths, it's going to look kind of whitish. But if you start focusing it in the region of red, the steeper and narrower these curves get, the more pure the red color gets, to the point where actually these lower curves, even though I'm drawing them in red on the screen, they would be something different and even more pure than you can see on your screen, just based on the limitations of your screen. So back to this additivity idea, you can add red up to this. A different way to answer this perfect red question is to say, well, what if I use a different red in this addition? So here on the top row, I've got a variety of reds. Hopefully John would agree that these are all red, but they're different, right? They're not quite the same red as that, they're different reds. If I add the same green and the same blue to each of those, you can see a variety of beiges. Now, maybe these all categorize as beige, but if you're trying to match the color of objects or the color of lights in a room, these color differences are probably not going to satisfy you. So additive color mixing is ubiquitous in color. Here's an example from a display system where you have 3 reasonably narrow band light sources, red, green, and blue, that again are mixed and matched to create different colors on the screen. One way to look at how they mix is in a chromaticity diagram, and I don't have a time to explain this fully, but this can be thought of as like the top view, kind of a color map of where colors are. And the triangle that you can draw between these points that represent the 3 colors give you an idea of what range of color space you could make with that display. And you can have displays with a smaller color gamut or a larger color gamut based on the bandwidth of those primaries. So a lot of the work that happens in our lab has to do with displays, display systems, how you choose these primaries, how you mix these primaries. And this is also applicable to lighting systems, which often have even more than 3 primaries. So here you'll recognize red, green, and blue in each of these lighting systems, but also other colors. Here we have some white, some broadband white spectra mixed in, which end up in the middle of the triangle. If you add other discrete colors, you get something that's a bigger polygon than a triangle. It has more shape available to you. And these get even more tricky because your vision is trichromatic, so it's easy to make a solution from 3 primaries to make colors. But if you have 7 primaries or 11 primaries or more, then there's many different ways to blend those to get to the same color. And then you have to look deeper at what you're trying to do with spectral matching or color rendition or other things. So these are critical to ongoing research in our group, and just enough to give you an idea what red light is all about from our perspective. Thanks.
Thanks, Mike. That's pretty interesting, and I hope that this so far is giving you an idea of the smorgasbord that we're hoping that fluorescent that this whole thing can become. We're going to continue now with something completely different. Here we have Robin Myers that is going to be talking to us. Robin considers himself to be a color geek. He's a fine art photographer, and he's a chemist in the manufacture of color charts and software for color acquisition and analysis. He's the creator of Chromaxion.com, which is a repository for the spectral library, and author of publications related to color imaging, and a holder of 5 patents on color matching, including one for Apple's first ColorSync color matching system. Take it away, Robin.
All right, as mentioned, I do maintain a library of something called the Spectral Library, which is a collection of all kinds of colored materials that I've been able to get and measure. And as I go through this, I was asked to show a little bit about how the measurement works. This is an instrument for measuring color by contacting it with the surface, and it has its own light source and so forth. This is a spectrometer which measures things by just pointing at them like a camera, and it measures the spectra. And as I go through these objects, some of them were measured one way, some other ways. But here is the first color that I came up with for the perfect color, the perfect red. This is a red M&Ms. I did a whole project of measuring over about 30 different colors of M&Ms. And this was the red from it. And it looks red when you see it, but it's really rather dark. And we can see that because in this spectrum, we can see that the red is just not reflecting more than 50% of the light. And it has virtually nothing else in here, but it's all dark. That's what we see. Another red that I went to for a familiar object is a red Lego. And this is much redder. We can see it comes up a little bit more. And this diagram here shows that it has a longer distance out from the center, which is gray. So that means it's a little more colorful than the other one. And this object is definitely red, and people see red when they step on them in the dark, if you have kids. Here's the two of them compared to each other. We can see, yes, indeed, the red Lego is indeed redder than the red M&M and more colorful. Here's a familiar red, Coca-Cola red. It's actually so unique, it's been trademarked, and it actually is called Coca-Cola red. It doesn't have any other designation. We can see it's nice and colorful. There's very little other wavelengths coming in to change its color. It's just all red wavelengths. Here's another red. This is one from Star Trek. If you remember, if you wear that color red, you're going to die, is generally what happens. But it's also a very colorful red, but it has a little bit of blue and violet reflected in here. So it has kind of a little bit of a magenta tinge to it. Here are those two compared. And we can see, yes, the Star Trek one, although it has more colorful in the red region, in the violet region, it again makes it look a little bit more magenta compared to the Coca-Cola red. Here's a couple of artist paints. I asked 2 artists which paints they liked for reds, their perfect red, and these were the 2 choices. And we can see that one of them is shifted over a little bit, which means it's a little oranger than the other one, and what you call warmer red. And here we can see the 2 compared against each other. Yes, quinacridone red is a little oranger compared to naphthol red, or naphthol red is a little more bluer compared to quinacridone. They're not too far apart here, but we can really see the difference when you compare them. Here's two other reds that artists proposed to me as being the perfect red. Cadmium red and quinacridone red. The cadmium red was chosen by a fellow who actually makes his own color charts. And that was his red, and it really looks bright and brilliant when you see it. But when you compare it here, you can see it's actually darker than the quinacridone red. But it's also less magenta-like. And these colors may not appear the same as I'm seeing them on your screen, depending upon how you've color managed your screen, or if you've even color managed it at all. But you can see the spectrum, and the spectrum will show you which way things are moving. Here is the US government, one of their reds. They have a standard for reds called 595. And in it, number 12199 is a really bright red. We can see it's very far out here. Lots of red here, very little blue in it. It's, to my eye, it looks just a little orangish though, and that's probably because this slope here is off to the left of some of the other reds that we've looked at. Here is another one from that same book, an even brighter red, but this line here is definitely a little bit more to the right. And we'll compare the two here. And we can see that this is the 38905 and this is the 12199. So we've got a little bit of difference. Even though they're pretty close, this blueness in here does show up, and the 38905 to my eye looks a little bit more magenta than the 12199. So the question is, what red is the perfect red? Well, they're all very closely related. We can see that they all kind of fall in a little group out here. So it's a narrow angle that's reds, but which one's the perfect one? These are all the reds in this selection of 28 different reds that I went through from my spectral library. And which one is the perfect red? Well, here's the reds I just showed you on these different slides. Basically, I came down to the conclusion that pick it. It's your choice. Everybody has their own choice for what is the perfect red. So find one of these and that's your answer. And if you want to play with the spectral library itself, look at these spectra and work with them yourself, you can go to the website chromaxion.com and to the spectral library, and you'll find all of these things there and lots more. And there's also some white papers there on other imaging topics, if that might be helpful to you. And that's it, my presentation.
Well, thank you, Robin. I think that we can all agree that he has earned the title of Color Geek. Shen received his bachelor's degree in science in gem and material engineering from Hebel GEO University and he achieved his master's in gemology from China University of Geosciences. He's currently working on his PhD in the Munsell Color Science Lab at Rochester Institute of Technology, and he's majoring in color science. Take it away.
Thank you, John. Thank you for your introducing. Hello, everyone. My name is Zhen Che, and I'm currently a PhD student at Rochester Institute of Technology, Munsell Color Science Lab. So it's really a great pleasure to be here today and give you guys a short talk about what is the ruby red. So ruby is the most valuable variety of corundum mineral species. It can command the highest per carat price of any color stone. So this makes ruby become one of the most important gems in the color stone market. So there are lots of factors can affect the value of ruby, such as the size, the clarity, cutting quality, and the most important one, the color. So the most famous ruby, as you can see from this figure, is typically formed in marble. This white surrounding area is the marble. So they are finding the layers that are distributed irregularly within the surrounding marble. Marbles forms as part of metamorphic process, providing the high temperature, high pressure environment, which helps to form the ruby. So let's look at the chemical composition of the ruby. So the chemical composition of the ruby is aluminum oxide. If we view in ruby from the perspective of crystallography, it consists of many basic octahedral units. So the aluminum atom is surrounded by the aluminum atom is in the center. The aluminum atom is surrounded by 6 oxygen atoms. In its purest form, the mineral corundum is colorless. But trace elements sometimes become part of the mineral's crystal structure, which can cause the variation of its color. For example, the chromia is the trace element that can cause ruby's red. So the more substitution of the chromia, the more saturated red color we can get. However, minerals can get lots of different trace elements from our Mother Earth, right? Some trace elements could affect color in the certain range. For example, if we add some iron and the titanium elements in the ruby, it will become more bluish. If we add a little magnesium element in the ruby, it will become more orangeish. So this image shows the red color of the ruby, and we might have a question that, what is the best ruby color? I know this might be very subjective question, but in the jewelry market, people do have some preference, and the most valuable ruby is the pigeon blood. So the pigeon blood is not like the killing this, the lovely bird to check the color. Actually, the pigeon blood represents the color of its eyes. So about 800 years ago, people found this pigeon blood ruby in Burma. Historically, we call it Myanmar, and suddenly it plays very important role in the market. Now we could also find this pigeon blood quality ruby in the other geographic origins such as Mozambique and Madagascar. But lots of people still believe that the ruby from Burma is the best. Here we could give a simple summary of pigeon blood ruby. First, no orangeish and bluish in color science area, and also Lina talked about the unique red. So we use the unique red to describe this. Second, the higher chroma value. Next, we don't like the color is not too dark, which means we pretend to have like a higher lightness value. Last but not least, the strong fluorescence, as with our topic Fluorescence Friday. The strong fluorescence is also important, but the too much iron in the ruby could inhibit the fluorescence. So this image shows the ruby with different level of fluorescence under the ultraviolet light. So when people viewing the ruby under the daylight, the daylight have some ultraviolet, the ruby will show much more colorfulness due to the fluorescence. This is ruby, but I also have a question for you guys. Is pigeon blood the best color among other red gems? Let me give you another example. This image shows the most expensive red spinel is another gem material. So might suggest this color is the best red in spinel. Like pigeon blood, this red spinel also have a commercial name, the Jedi. I have seen some example of this stone when I was working in the industry, and I should tell you guys, this color is definitely not unique red. It shows slightly bluish, but with super strong fluorescence, like neon light. It seems we have a different criteria to evaluate not only the red color, but also other color in gemology. Color is a really amazing topic. People do have different kinds of red as well as different kinds of color. That's the reason why our life is so colorful. Thank you very much. I hope you enjoy my talk, and yeah, may the force be with you, right? And if you guys want to know more information about the gem and gems in color, please check this website. Thank you
very much, Shen. this is such a great opportunity, I think, to get to hear about the color red from so many different perspectives. We see how color affects all these different disciplines. Eddy, could you take over the screen now, please?
So of course, here it is.
Excellent. Eddy is the next guy up, Eddy Hagen. He started his career in the printing industry way back in 1988. For a long time, he worked at the Innovation Center for the printing industry. Although now working in a different industry, he still shares his print and color related insights in the blog that you see at the bottom of the slide, insightsforprint.ceo. Take it away, Eddy. Oh, hang on one moment. The chat box is open, as I said before. Start thinking about questions. I see we have at least one question in there and a lot of wonderful comments. Keep the comments coming and let's have some questions. Take it away.
Okay, thank you, John. Let's take a look at one of those iconic reds, the Coca-Cola red. But first, before we start, in printing we use subtractive colors, and thanks to Mike, we know what that is. And the standard ink set that we are using is CMYK, cyan, magenta, yellow, plus also black, which we also call process colors. Now, process colors is not the only option. There is also an option to use spot colors, which means that we use just one ink for a very specific color, like here, for instance, the red. And the most well-known example of spot colors are the Pantone colors, like this red 32C. You can simulate those spot colors with CMYK. Those are the numbers that you can see under color values, but it has a disadvantage that it looks a little bit, it can look a little bit different, like as you can see in this picture. And so why should one care about process colors versus spot colors? Spot colors are easier to control on a press. You only have to control one ink, not 2, 3, or 4. And if you look at brand colors, the rumor says if the brand color in the shop deviates from the expectation, consumers will not buy the product. And the maximum deviation that the same rumor specifies often is 2 delta E 2000 from the ideal color. Those of you who are not familiar with delta E, it's just a measure unit to specify color differences. So let's look at the iconic Coca-Cola red. It is iconic. It is their second secret formula. There is no Pantone color for Coca-Cola red, but when you see it, you know it. Really? Always question statements like that, dear students. Please do remember that. Question those statements. And that's what I did in a test, a color memory test. I showed 6 variations of red. I showed them in sequence, so not next to each other, which makes it a little bit more difficult. And every one of those 6 colors was a unique brand color. Next to Coca-Cola was also Adobe, KitKat, Netflix, Target, and Vodafone. The last figure that I got was 372 people participated. And which color did they choose from these 6 variations? It's a mixed bag of results. There was not one clear winner. There were 4 colors that were more or less equal in choices. So that iconic color, people have different memories of that. You can't remember an iconic color, not even the Coca-Cola red. Now, back to that statement that this will influence, color deviation will influence buying. I did a survey with over 100 people, and I used the same colors that you just saw, but I took a different question, which was, which one would you not trust? So a negative question. And if you look at it, almost 2 out of 3 would accept all of those colors, even though that the deviations are up to delta E of 9, so much higher than the delta E of 2 that is what is often said to be a maximum deviation. So depending on the question that you pose and the people you ask, you can get very different results. And this is part of my collection of Coca-Cola cans. These are regular cans, but over the years, you can see deviations. When I started with the collection, it was more orange. Now it's going to more bluish. So it can really shift. Also, never forget that lighting can be a part of the total experience. Probably those cans are the same color, but the lower shelf, it doesn't get the same amount of light as the upper shelf. So the color that you see is different. Here they are on the same shelf and they look very different, but probably the person who filled the shelf didn't notice. So do people really notice that? Also, the winter version is darker. This is specified by Coca-Cola. And if you look at the cans, sometimes, at least here in Belgium, they use metal cans. Those are printed with opaque inks, but sometimes we also have aluminum cans or aluminum cans, and there they use transparent ink. Now, this will definitely give a different color impression. So, what is Coca-Cola Red? Which one is it? Also, a six-pack, the shadow makes it a little bit darker. Another view of the six-pack. I'm going to shift it a few times. You see those spots? Those are very different colors. That's much more than 2 delta E difference. But you wouldn't notice that in a shop. And that's also, this brings me to my last point. You have to design tests very carefully. And there have been a lot of tests on the perception of color differences. And usually it's just a few samples are shown and you see a different color. Now I designed the test, a student executed it. We had both flat samples and folded boxes. And what was unique in our test was that it also included an identical copy. And what was one of the findings? That almost one out of 3 print professionals saw a difference between 2 identical copies. Now that's amazing. And why is that? It has to do with psychology. They are color experts, they know color, and if you ask them, do you see a difference in color, they will notice it. And this is what is a little bit wrong in the printing industry, that we are looking for things that are not there. And this made me formulate the uncertainty principle of visual color evaluation. If you know that you're evaluating color, you can't be objective about it. And to make it even more extreme, when looking at folded boxes, it was 2 out of 3 that saw a difference between 2 identical copies. So that's really amazing. And the reason was probably due to difference in lighting. And I'm switching here with between 2 pictures. The one
We're getting
box,
close to time.
Yep. The one box is shifting a little bit, and the red is darker when it's shifted a little bit. So lighting is also very important. So conclusions: don't try to be more Catholic than the Pope. Do question bold statements and design tests very carefully, especially because you are students. And that is the end of my talk. Thanks for listening. That's my blog, and a must-read book, Thinking Fast and Slow by Daniel Kahneman, who also got a Nobel Prize for economics. This is really worth reading, because if you want to design all kinds of tests and studies, you have to read it as a background. So thank you.
And thank you, Eddy. I think we can agree that today's sessions have been a smorgasbord. We have talked about a lot of different topics. Eddy just talked about branding. We talked about gemstones. Robin shared his collection of different reds. I talked about the different sorts of things that aren't really red. And Mike talked about what red is in terms of displays. Lina gave us a number of different topics, including what unique red is. questions are appropriate at this point. I think I'm going to turn over to Jean. Is that right? Jean, do you want to lead the
Yes.
question?
Yes, I'm the question.
Excellent. Thank you.
Is Lina on the call? Because the first question
Yes.
is for her. Okay, great.
Yes. Yeah.
The Nader says that he noticed that the mean of the chosen unique hues by subjects appeared to be orthogonal, approximately 90 degrees apart in Munsell in your first section of your presentation. Did this orthogonality show within each individual observer? Or was it simply a trend across the observers when they're all put together?
It was a trend when all the answers were put together. In fact, there's a wide variation between the angles between one hue and the other. And as a part of the study, we also check if those angles had to do anything with the capability to differentiate small differences, small color difference. So we also did a test with the Farnsworth Munsell tips to see if there was any correlation, but with the angle and the mistakes that were made, but there was no correlation that we found. So it was just an average. But there's a lot of variation.
Thank you very much. That's very interesting. Another question from Nader has to do, it's really more of a comment, but I think we can get Eddy to comment on this. And that has to do with the metameric matches that result from the formulation of the Coca-Cola colors using different types of ink and different materials. Do you have any information on metamerism, Eddy?
I can say that this is indeed a good remark, because it is an issue, and this is one of the many issues that we still have in printing. Many print samples are printed on an inkjet printer, for instance, and they should resemble the print that is eventually printed on an offset press, for instance. Now, if you're using exactly the right lighting, they will look the same, but the difference in lighting, if it's not D50 or D65, you will get differences in the color that you will see. But this is just one of the many things that can be wrong in the printing industry. So there are lots of opportunities for bright students.
Lots of opportunities for bright students. Did everybody hear that? The next question is for John from Emily. I think of brown as a dark red or dark red-orange. Perhaps the people who named the animals were smarter than we think in terms of color identification.
Yeah, well, I would agree that the comment about brown as being a dark red or a dark orange, which is an odd thing. I mean, you wouldn't say dark orange instead of red. It's just not, it doesn't make sense linguistically. But yeah, that's perhaps another explanation for why colors were misnamed, or objects were misnamed in terms of their color previously.
So if you haven't already done so, will you please put your university into the chat? And we only have 1 minute. So does anybody have one final burning question?
I have a question for Robin.
Yes.
Robin, could you tell us what your research is going with what you're measuring next? And you already said it's available to us to check into these measurements and how we could use them.
Well, I've just finished translating a Russian book on color from 1956, and it has thousands of colors, which I'll be measuring and putting up. And I just took delivery of a Ostwald color album, which I will probably measure and put up. So I have lots I have thousands of samples, tens of thousands, and I just haven't had the time to get to them all. So if anybody wants a particular sample, let me know. If it's legal, I'll do it. If it's not legal, well, so don't ask for Pantones or Color Curve or RAL or NCS, because those are all protected. But anything unprotected, I'll get it for you if I can. Oh, I just finished measuring some fruits and vegetables. I'll be putting those up soon too. By the way, those are very difficult to measure, by the way. You can't measure them with a contact spectrometer.
Thank you, Robin. Luann and John, we've passed the 4 o'clock mark. Would you like one final comment?
Luann?
Oh, my comment would be, first of all, thank you so much to everybody. We love seeing where you're from, because remember, all of you, this is our second presentation, second Fluorescent Friday. Our whole idea is to learn from everybody around the world and join forces and share information. So we're trying out our mini talk format, and we're going to be asking for you all, students, to be able to share in your research. So look for that coming up. And, if you do join the ISCC, the membership is very inexpensive for students, so that you can get updates on what we're doing. But I just wanted to say, we want to know the topics you're interested in and different approaches. And we're going to be wanting to set up a platform where we can actually talk to each other in between formats. So anyway, I just thank you to everybody, and and really, really appreciate your input. How about you, John?
I think this has been fun. One thing that I have very much appreciated from being involved with the ISCC is getting a chance to meet various people that are on the call here today, and to learn more about the artistic side. I grew up in the silo of printing, so I understand that, and there's a lot of stuff about color that I understand from that, but picking it up from different perspectives is such a cool thing. And I hope that the students have enjoyed that part of this today. And we look forward to having student presentations in the future.
And we have a date for that, Lina, right?
Yes, our next event is Friday, April the 23rd. And we will be having mini talks about what's new in the color field. And we hope a lot of university students can participate, working from science, design, and communication.
Exactly. Yeah, so we're just so happy that you guys are part of this. And we all feel, as John said, and everyone has been saying, in order to think about color as a multidimensional phenomenon that it really is, we want to be able to bring forces in from the arts, from the sciences, from design, from psychology, from all of them, because I think it makes the whole topic richer. So yeah, look for our information, our emails going forward, and we will look forward to hearing more from you. So, thank you so much.